So good afternoon, everyone. I'm Sama Saeed, an assistant professor at the City College of New York. And this work was done with the help of my graduate student, Nikita Acharya. Unfortunately, she wasn't able to attend today. So in this presentation, we propose test circuit design approaches to monitor circuit error rates. We also propose an algorithm to automatically generate these test circuit for a given quantum algorithm. And so this is the outline of my talk. And first, I'm going to motivate this presentation. And so we all know quantum computers are susceptible to different types of errors. And one of these error type is gate error, which is modeled as poly-error channel. Now, in order to understand how these polygates or poly-error propagate, and spread into the quantum circuit, we define the Clifford gate, which is a special or a subset group of quantum gates, which has very interesting property here that they transfer poly errors to poly errors. What that means is that the poly error can propagate through the Clifford gate, and also the propagation path is guaranteed. And so you can see here some examples of how these poly errors can propagate through some of the quantum circuits, some of the Clifford gates. And so the main problem that we face is how do we handle errors? And there's two approaches to deal with errors, right? One approach is to use quantum error correction. However, the main challenge is the requirement or the need for large number of physical qubits, which is not possible, at least for near-term quantum devices or missed quantum devices. The other approach is to rely on noise-aware quantum compilers to mitigate errors. And one of the main compilation approach that significantly affect the fidelity of the quantum circuit is the quantum circuit mapping, in which we take like the logical quantum circuit and map it to satisfy the physical constraints of the hardware with the objective of maximizing the success probability of the circuit. We may use a very simplified success model during the compilation, such as the estimated success probability. However, we still have the main challenge, which is the absence of accurate failure model to capture temporal and spatial variation in the circuit error rates. And because of that, many people have been looking into how do we accurately characterize the error rates of the hardware. So for the interest of time, I'm just going to look into some of these approaches that are more interested in characterizing the error rates of a given quantum circuit instead of the entire quantum hardware. So there's a lot of work related to, or some works that has been proposed in the past year and a half or 2 years related to assertions, where you need to test the state of the qubits, or you apply, for example, a test circuit in which you check whether the qubit is actually in a certain states or not. The main disadvantage here is that these are like limited to qubits at certain states. There are other existing work that relies on the concept of uncompute, or some people call it mirror gates, where you take a subset of the gates and you uncompute them, so you can construct an identity matrix, and you use that subset to somehow infer the error rates of the quantum circuit. To avoid some coherence error, you may want to ensure that the depth of the circuit is less than or less than or equal to the minimum coherence time of the physical qubit. Again, when you think of larger quantum circuit, the cost and the overhead of the uncompute will also increase. And eventually, if you don't want to really introduce so many coherence error, you may end up having a limited gate coverage. So you will only be able to test few subset or certain regions of the circuit. There is also another interesting work, and this is more on the fault-tolerant quantum computing domain, which is the flag method for quantum error correction. And so, as we all know, in quantum error correction, we encode the logical qubit into physical qubits, and then we use a syndrome extraction circuit to detect errors in these physical qubits. And this is a naive example of how you can build like a syndrome extraction circuit with a single ancillary qubit. However, the ancillary qubit itself is also noisy. It can produce errors. And so when you apply this flag method, and by measuring the flag qubit and ancillary qubit, you can capture these correlated errors in order to correct them. So based on the concept of the flag qubits, we proposed this test circuit design, where here flag qubit correspond in this slide to ancillary qubit, or what we call it NZILA. And unlike the flag method for quantum error corrections, we target universal quantum circuits that are executed on NISQ devices. So the idea is simple. We entangle the ancillary qubit with the circuit. We take a small subcircuit of the quantum gate, uncompute them, and then unentangle the ancillary qubit. Based on the circuit design, you can see if there is a bit flip errors, it can propagate to the ancillary qubit upon measurements. We can also slightly modify the circuit in order to be able to propagate the phase flip errors also toward the measurements. If we want to minimize the impact of coherence error, we ensure that the depth of this test circuit, again, is less than or equal to the minimum coherence time, which is feasible because, again, you're uncomputing only a small subset of gates, unlike the uncompute, where you have to uncompute the entire circuit, at least from layer 0 all the way to your test points. One interesting aspect here is that, of course, the UN may consist of both Clifford and non-Clifford gates. And so in that scenario, you may not guarantee the error propagation path. And so you may also design your regions to include these Clifford gates, which are primarily the CNOT gates only, to ensure this propagation path. And so the next question will be, how do we actually generate these test circuits such that we can cover as many gates errors as possible? And so the first step will be to take the circuit and divide it into regions and then test each region. And so to do that, we have to first identify free ancillary qubits. So we construct like a coupling subgraph or a coupling graph for this subcircuit, and then look into all these adjacent free ancillary qubits. And we simply select the ancillary qubit that requires a gate with a minimum error rates to be entangled with your allocated physical qubits of the circuit. And so in this example, we consider that qubit as Q4. The next step would be to identify what are these gates that need to be uncomputed. So we can simply model that, represent the subcircuit as, again, a gate dependency graph now, and identify all these reachable gates from the ancillary qubits to uncompute them, unentangle the ancillary qubits, and perform the measurement. You can design the same circuits if you want also, since using the same approach, if you want also to detect like phase flip errors. This one is primarily for bit flip errors, so you repeat the process for different regions. And so the question here is, how do we assess how good are these test circuits? So we use a gate coverage metric that looks into how many of these gates are actually covered by the test circuits, by all the test circuits. And in the evaluation phase here, what we actually did is that we use a quantum compiler to allocate in physical qubit and generate the corresponding physical quantum circuit with a very high estimated success probability. We call this physical quantum circuit as a high ESP mapping circuit. And then we search on the coupling graph of the quantum hardware for an isomorphic subgraph that has a low estimated success probability now. And we call the generated circuit as a low ESP mapping circuit. Then we introduce the same set of test points to both physical implementations of the same circuits, and we execute these test circuits on the quantum computer. And so we compute what we call it the number of effective tests. And so here we look into how many of these test circuits in which the high ESP mapping physical implementation of that test circuit give you higher success probability than the low ESP mapping circuits. And so using this number, we can compute this percentage of effective tests. And our argument here is that if this percentage of effective tests is large, then we can actually rely on this quantum compiler and consider that this high ESP mapping circuit is the one that gives us better results. If this percentage is low, it is very low, below than 50%, then we can actually rely on low ESP mapping circuit. We see that there is some drift in the error rates, or we can actually generate another set of qubit allocations. And so in the experimental result, we try to evaluate these ideas and the effectiveness of these test circuits. And so we use several benchmark circuits executed in Melbourne quantum computer. And you see in this column, this is our proposed approach. So we measure actually the percentage of effective test and also the coverage matrix. And the key point here is that by looking into the percentage of effective tests, we can always select the qubit allocation that give us highest success probability when you compare the low ESP mapping and the high ESP mapping physical quantum circuits. We compare that with these approach based on assertion and the uncompute, and we see that these approach in few cases actually fail to select the qubit allocation and the physical implementation of the circuit that gives you the higher success probability. The only limitation here was that we have limited coverage. Again, that's not only because of the coupling constraint, but also because we're looking into two isomorphic subgraph, and so the test circuit themselves has to be isomorphic, and that reduced the candidate or the number of potential candidates for the ancillary qubits. And so to improve the coverage, we applied both approaches. So in fact, we apply our proposed approach for those regions that are not covered by these uncompute or assertion-based approach. And for this yellow line, you can see we can improve the coverage. Still, when you look into percentage of effective test point, when it is large enough, or when you look into the percentage of effective test point, you can always actually in these data select the qubit allocation that has the highest success probability. One last experiment before I finalize my talk is that here we repeat exactly the same analysis, but we said, okay, we're not going to restrict our region to Clifford gate. We're going to allow both Clifford, non-Clifford gate and see what happens. And surprisingly, we found that if the circuit is large enough and if these two isomorphic subgraphs significantly differ in their success probability, we can actually rely on our proposed approach to select the qubit allocation that gives you the best results. And so with that, I can conclude my talk. So we proposed this generalized test circuit design approach using auxiliary qubits based on this concept of flag method. We also proposed this automated test methodology to generate these circuits. And the argument here is that we want to cover regions that may not be covered by existing uncompute or assertion-based test circuits. And we show the effectiveness of this approach through some initial results in the experimental section. So thank you so much for listening, and I'll be more than happy to take questions.
Oh, thank you so much. Any questions? So I think one question, I mean, you pointed out the connection to error correction and the use of the flag qubits, but if I'm understanding, there's not the decision-making process that, you know, error detection normally requires feed forward to do the correction process. I mean, this seems to be, it doesn't have that requirement. That's right, isn't it?
Yes, I mean, are you talking about our approach, right?
Yes, that's right. Yeah.
Yeah. So we're not actually correcting any errors. So let me put it in another way. So one main advantage you may think about, I mean, using our approach for, is that when you do the sampling, for example, so you execute the circuit on the quantum hardware and you get some noisy results. So if you actually measure these auxiliary qubit, it may help you to filter some of these noisy results. I mean, we didn't do that. This is something we're actually trying to do and see how good it is compared to the error rates of the CNOP. But for now, we just like use two different qubit allocation for the same circuit and see, okay, by seeing how by measuring or monitoring different points of the circuit for two different circuits that has exactly the same implementation, can we select blindly without knowing what is the output, which one of them is actually giving us a good result. But yeah, we don't do any correction, and I think that will help us to improve the sampling of the output.
Well, okay, I do agree, but I also think it means that these methods can be tested today, that the technology can support this now, and you don't need to wait for the feed forward operations and these types of things.
Yes, that's exactly true.
Have you made plans to do testing on specific hardware, or?
We are actually. So the results that we show, these are all tested in IBM Melbourne. At the time when we did the experiment was actually last year. And so we only had access to Melbourne. But currently, we recently had access to another IBM machine. It was 16 qubit, I think, or something. So we're trying actually to see how good it is in terms of the sampling, actually, without the need to search for any isomorphic subgraph. And does it actually help improving the success probability of the expected output?
Okay, excellent.
For different applications.
Well, thank you very much, Sama.